Today is an exciting lecture because we're starting the section on the moduli of stable curves after going through sites sheaves and stacks, and then algebraic spaces and stacks, and then the geometry of the Lie-Mumford stacks. We're at the fourth part of the course. We're going to begin discussing MG and MG bar with the goal of showing projectivity of MG bar. And we'll have around 6 or 7 lectures on the moduli of curves. And today's focus is mainly on nodal curves. But before that, I would like to take sort of give a lengthy recap of the Kiyomori theorem, and then we'll move on. We'll give a refresher on smooth curves, and then talk about nodes and nodal curves. And to recap here, let me first just remind you of the definition of a coarse moduli space. I don't know why it's way down here. So a coarse moduli space is a morphism from an algebraic stack to an algebraic space that satisfies these 2 properties. One is that induces a bijection on all geometric points. In particular, the topological space of the stack is identified with the topological space of the algebraic space. And it also satisfies a universal property for maps to algebraic spaces. And specifically, any other morphism to an algebraic space factors through the map 2x. And so we're interested in this because we are willing to sacrifice some of the universal properties of an algebraic stack in order to get a more familiar object. Here it's just an algebraic space, but later we want to show that it's a projective variety in the case of MG bar. And one of the main theorems, in fact, of the entire course is this Kiyomori theorem, which I stated and proved last time. And let's walk through the hypothesis here. We take a Lie-Mumford stack, and it's separated in finite type over an Ethereum base. And with those hypotheses, you can conclude that there exists a coarse moduli space. And then not only that, you have some other nice properties. You have this and sort of very useful additional properties of the coarse moduli space map. And maybe I should highlight one of the key hypotheses here is the separated condition. Is that X is separated. Here, what that means, remember with our definitions, it means that the diagonal is proper. But since X is the Lie-Mumford, we already know that the diagonal is quasi-finite. Well, it's even unramified. And for a morphism of schemes, proper and quasi-finite is equivalent to a finite morphism. So this implies even that that X is, for a Lie-Mumford stack, X is separated if and only if the diagonal is finite. And so, and later, we will show that the stack of smooth curves, as well as stable curves, which we'll define, are separated. And we'll use the valued criterion. But the upshot is that the Kiyomori theorem then implies that there exists a coarse moduli space, where this is just an algebraic space at first. Right, and the Kiyomori theorem is one of the, I would say, is one of the main theorems of the entire course. It's what lets us get started to construct an algebraic space that we then show as a projective variety. And due to its importance, and since I covered it last lecture, I'd like to give sort of a systematic review of the ingredients that went into the Kiyomori theorem, and at the same time explain how similar methods give the general Kiel-Moore theorem. Right, so I'm going to separate this next slide sort of into two different parts. On the left-hand side, I'm going to discuss the Deligne-Mumford case of the Kiel-Moore theorem, which we discussed in detail last Wednesday, and we gave almost a complete proof. And on the right-hand side, I'll discuss the general Kiel-Moore theorem. And like the basic hypothesis and setup in both cases is that we have an algebraic stack that we're assuming is a finite type, and finite type over an Ethereum ring. Right, and in the Kiel-Moore theorem, let me give a slightly different formulation than on the last page. That, well, yeah, so I'll say that if the diagonal is unramified and finite, then there exists a coarse moduli space. And keep in mind here, the unramified condition is playing the role, is the condition that the stack is Deligne-Mumford, and this finite is the condition that X is separated. But the general Kiel-Moore theorem is the following: that all you need is to know is that the inertia is finite, then there exists a coarse moduli space. And here, maybe let me just recall that the inertia is the fiber product over the diagonal. So certainly if if X is separated, certainly the inertia is finite. And right, and but this distinction between the diagonal being finite or the inertia being finite didn't really play a role in our proof. Like we could have handled the inertia being finite. The main condition that we were really using was the Deligne-Mumfordness, namely that the diagonal was unramified. And in fact, there's even a more general version of this theorem. You can drop the finite typeness hypothesis, and you can work over non-Noetherian bases, but we'll ignore that. Okay, so to sort of summarize our proof, let me give sort of a sketch of the argument, consisting of several components. So we're going to start with, let's let X be a geometric point. With closed image. And so K is algebraically closed. And what we're trying to show is that there's an open substack around this point that admits a coarse moduli space, and then we glue them all together. So the first step of this argument is one. Well, let's let U to U be an arbitrary smooth map, a smooth neighborhood of our point. We know this exists because it's an algebraic stack, and then this is essentially the argument that we use to show that if the diagonal is unramified, then it's in fact Deligne-Mumford. What you do is you then slice U to arrange that you have U to X, to arrange that you actually have an étale cover, and then by throwing away all the other preimages, you could arrange that that you have a Cartesian diagram where the preimage of the residual gerb, or the classifying stack of the field valued point X, is just a point, where this is Cartesian. Right, and in the more general case, in fact, the same exact argument, the same methods, shows that you can arrange to have a neighborhood that's not étale, but it's at least quasi-finite and flat with the same Cartesian diagram. Okay. And now once you have an Étale neighborhood on the left-hand side, that's what we used in order to construct a local quotient presentation. And it worked sort of as following. Let's let D be the size of the stabilizer group. You know, it's a finite group, abstract finite group. And then we considered the d-fold fiber product of U over X, which is just U over X, dot, dot, dot. And then we removed all of the diagonals. So we defined W this way. This is just the complement of all diagonals. And so this is a quasi-affine scheme, and it has an action by the symmetric group SD by permuting the factors. And we realized that the quotient stack parametrizes diagrams where, you know, you have the fiber category over a scheme S consists of a morphism to X and a closed subscheme of the fiber product such that this map is finite Étale and of degree D. And then what we showed was that the map from W mod SD to the stack X is Étale and representable. And moreover, yeah, that there was a point W mapping to X, inducing an isomorphism of automorphism groups. Okay, and finally, okay, maybe I'm getting too detailed here. You can arrange by shrinking that W is affine, and if you want, you can replace SD with the stabilizer. All right, and that was the argument giving us a local quotient presentations for Deligne-Mumford stacks, and to handle the general Kiyomori theorem, you need a different argument. So you replace this with something similar, but it's more technical. Zooming. So you consider the Hilbert scheme, or the relative Hilbert scheme. Let's call it H, parametrizing sort of diagrams. So an S value point of the stack is going to correspond to first a morphism to X. And then a closed subscheme of the fiber product where this map is no longer Étale, but it's finite and flat and degree D. And, but yeah, so you need to use this relative Hilbert scheme, but it's, you know, since U over X is representable, there's no real issue in constructing this Hilbert scheme if you rely on the existence of Hilbert schemes in the case of schemes. And then once you have this, the universal family of the Hilbert scheme, what it gives is it gives a morphism from H to X, as well as a closed subscheme of the fiber product. Let's call that W, such that this map is finite flat. And note that you can, since U to X is representable, W is even it's a scheme, and you can even arrange it to be affine. And moreover, this map here is what you've constructed. This map is Étale and representable. And sort of by construction, there is a point W in here mapping to X, inducing an isomorphism of automorphism groups. So we're sort of in the same situation as in the Dely-Mumford case, but we've gone from these finite étals to finite flats. And we have an étal cover. On the left-hand side, we have an étal cover that's an honest quotient stack by a finite group. On the right-hand side, we have just H is just an algebraic stack, but it has a finite flat cover by an affine scheme. And that's going to sort of play the analogous role of the quotient presentation. Okay, moving on. So here I just recapped the two versions of the theorem, and in red you see basically what stage we're at right now. And then now the arguments really proceed along the same lines. So the next step was to show that in the special case of a quotient stack that we have coarse moduli spaces. So we showed that if you have a finite group acting on an affine scheme, that the morphism to the invariance is a coarse moduli space. And note here that this is the same as the global sections of the stack. And an analogous argument on the right-hand side is you need to show that stacks that have a finite flat cover by an affine scheme have coarse moduli spaces. So here, right here we have H, and we have a W, which is affine, and this map is finite flat. And if you take the fiber product R, then this is you get a groupoid, which is a finite flat groupoid. And what you need to show, and in fact, it's a very similar argument, you show that the morphism from H to its global sections is a coarse moduli space. And keep in mind that the global sections here is identified with the 8R invariance of the ring A, namely functions on A such that the two pullbacks are equal. Right, so that was sort of the local case in both sides. And then we needed to use the finiteness of the inertia. So the fourth step was to use that the inertia is finite to arrange that these local quotient presentations not only preserve the automorphism groups at the particular points, but preserve all stabilizer groups. That is, induce isomorphisms on stabilizers at all points. And this is where we use the finite of the inertia, because that gave us, and on the on the right hand side, it's the identical argument. And then in order to reduce, so this was one of the steps in the reduction to the local case, and then we needed to show. So we basically showed the following statement, that is, if you have a morphism of DM stacks, let's say this is F, that induces a map on coarse moduli spaces. So we're assuming existence of coarse moduli spaces here. That in this setup, we showed that if F is a tau and preserves the stabilizer groups, then the induced map on quotients is a tau, and the diagram is Cartesian. And again, this step is identical in the general case. And then the last step, putting everything together, we have our stack X, where we're locally trying to construct a coarse moduli space around a particular point. We find in the tau neighborhood by a finite group, such that with this we know we have a coarse moduli space. And if you take the like the corresponding groupoid of stacks, then you argue that this has a coarse moduli space, so Roman R. And then you show that this is an Ital equivalence relation. And this implies that if this is Roman W, that this implies that W mod R is an algebraic space. And then if you reduce to the case where this W surjects onto X, then this quotient, this W mod R, is the coarse moduli space we're after. And in the general case, it's the identical argument. Right, so yeah, there you have it. That's a quick sketch of Kiel-Morey theorem. And it's a good time to stop for questions.
What type of conditions will guarantee that the coarse moduli space is a scheme?
Oh, that's a difficult question. Yeah, that's a difficult question. I mean, if you show it's projective, then you know it's a scheme, but yeah, that's sort of something that you often have to grapple with, that it's, yeah, we don't have that many methods at our disposal to show that algebraic spaces are schemes. I mean, you could show a lot of the projectivity criterion, amplitude criterion for line bundles do extend to algebraic spaces. That helps. And another tool you can use is Zariski's main theorem, which is that quasi-finite and separated morphisms of algebraic spaces are quasi-affine. So that's also a way you can show that an algebraic space is a scheme. But in general, it could be a difficult question. Other questions? Okay, so let's get on to curves. So I'm going to start slow, and we'll just start with a refresher on smooth curves. And since this is all familiar material that's either in Hartshorne or Vakil's notes, so I'm going to kind of go quickly through the smooth case. But so I want to at least say something, because when we introduce nodal curves and then stable curves, we want familiar properties. We want analogous. We want to generalize some of these properties to. So first and foremost, what do we mean by a curve? So curves for us are always over. What we mean is a curve over a field is just a pure one-dimensional scheme of finite type. And people's definitions of curves vary. Like, what do you want to? Yeah, with this definition, the spectrum of a DBR is not a curve, but that's okay. So we have and then if it's a proper curve, you define the genus of the curve by H1 of the structure sheaf. And we have these two general facts about curves that I'm kind of highlighting because it's good to keep in mind. If you have if C is a proper curve, it's automatically projective. This is also in Hartshorne. At least the smooth case is in Hartshorne, and you can reduce to that easily. And then the second fact here is I haven't proven this, and I don't think I'll even use it, but it's nice to know that if you replace scheme in the definition of a curve with an algebraic space, it doesn't change as long as it's separated. So if you have a separated pure one-dimensional algebraic space, then it's automatically a scheme. And for arbitrary integral curves, we have sort of this Riemann-Roch theorem, which is an easy consequence of sort of just of cohomology, that you can compute the Euler characteristic in terms of the degree and the genus. But the Riemann-Roch really becomes powerful when combined with Serre duality. And so Serre duality says that the sheaf of differentials is a dualizing sheaf, and since C is smooth, this is a line bundle. And we often write like omega C as the sheaf of differentials on a curve because it is the dualizing sheaf. And just to remind, the dualizing sheaf is something that so that it satisfies the natural pairing satisfies Serre duality. In this context, like for instance, what it tells us is that, like in particular, H1 of a line bundle is then identified with H0 of omega C, or the tensor L dual. And therefore, if you combine the Serre duality with the Riemann-Roch, you get this identification, which is a particularly useful form. And I should say, even for smooth curves, Serre duality is a deep theorem. There's really no, it's it takes work to prove no matter how you approach it. And then so using Riemann-Roch and Serre duality, we can get nice conditions for whether line bundles on smooth curves are positive, and so this is on the right hand side here. So if you take a smooth projective curve, then we have, like, if the degree is negative, then there's going to be no global sections. If the degree is positive, it's automatically ample. So the easiest ample criterion is on smooth curves. But then if the degree is once it's 2G, it's base point free. And then once it's even one larger, it's very ample. So let's just assume C is geometrically connected over K. And then if the genus is at least 2, we can use Serre duality and Riemann-Roch to calculate the global sections. So the global sections of omega C, of this either dualizing sheaf or the sheaf of differentials, by Serre duality is H1 of C of OC, which was by definition the genus. And similarly, H1 of omega C is identified with H0 of C of omega C. And because C is connected, that's just 1. And then if you apply Riemann-Roch applied to omega C, you get that H0 of omega C minus H1 of omega C is equal to the degree plus 1 minus G. And that allows you to compute the degree of omega C as 2G minus 2. In particular, it's always ample by this positivity criterion. But it's not always very ample, and so there you need to consider powers of the dualizing sheaf. So for K greater than 1, we can do the analogous calculations that H0 of omega C tensor K is 2K minus 1 G minus 1, that there's no H1, and its degree, well, it's just K times the degree of omega C, so that's K times 2G minus 2. And this implies that omega C tensor K is very ample if K is at least 3. Okay, next thing I want to remind you is what families are of smooth curves. A family of smooth curves and is a smooth and proper morphism such that every geometric fiber is a connected curve of genus G. Necessarily smooth because the morphism from C to S is smooth. And there's always this line bundle. The sheaf of differentials, the relative sheaf of differentials is always a line bundle, and this and it sort of behaved well that restricts under any base change, but in particular if I restrict to a point. So if I take this relative sheaf of differentials and restrict to the fiber over a point S, then this is identified with the sheaf of differentials of this curve S over the residue field. And one thing that we sort of used repeatedly in our arguments for MG already, namely that when we showed that MG was an algebraic stack, we used the following property of families of smooth curves that the sheaf of differentials, the relative sheaf of differentials, at least the third power of it is relatively very ample, because that could be checked on fibers. And moreover, like the cohomology and base change allow us to conclude that the push forward was a vector bundle. All right. Yeah, that's my quick recap on curves. We're now going to move to nodes. But I'll pause for questions. Okay, so what are nodes? So we'll start with a curve over a field, not necessarily algebraically closed, but if it is algebraically closed, we say that a point is a node if the complete local ring is isomorphic to this this power series ring. And here, just to remind you that we're going to use the completion a lot. This is just the limit of the thickenings of the maximal ideal. And in general, if K is not algebraically closed, essentially because like quadratic polynomials may not factor over that field, the complete local ring may not have such a nice structure. So the way you define a node is to say that there's just a node over the base change to the algebraic closure. And I think you all know this, but it's just the algebraic picture of a node is just a curve that intersects itself transversely. So this is sort of the algebraic, like one-dimensional picture. But if you want to view this complex analytically, then it looks like a node sort of looks like what happens when you take like a loop of a Riemann surface and pinch that loop to a point. So where like the node are these points here. Okay, so that's the definition of a node. And so one of the first things you need to show is that, I'll leave this as an exercise, is that if P and C is a node, and we're over a field that's not algebraically closed, then there exists a finite separable field extension and a point P prime in the base change over P, such that if I take the complete local ring of this curve CK prime at P prime, then it has this nice form. So in the definition of a node, we knew this was happened over the algebraic closure, but you can then go to a finite separable extension. And we also have the following very nice characterization of nodes is that I'll also leave it as an exercise. If you have a point of C is a node, then you can find an étal neighborhood of C. So this is étal, and a point U over P. And so that is also étal over the planar node. So this is just the plane curve sitting inside A2, which is the union of the two axes. And you could find an étal neighborhood here such that this point U goes to the origin in A2. And I leave this as an exercise because it's either a nice application of Artin approximation, or you can also do this directly without Artin approximation. But I don't want to cover it right now because we're going to prove a relative version later. But if you remember back at my motivation for the étal topology, this was sort of one of the motivating factors is that you can split branches of nodes in the étal topology. All right. Moving on, I want to give you the formula for how you compute the genus of a nodal curve. So suppose you have sort of a curve that looks like this in the right-hand side. So this has
in one of those exercises. Question?
Sure, go ahead.
In the exercises on the previous slide, there was the algebra, the first exercise, algebra formal series in K. Is that supposed to be K prime, or should that be the original field K?
Oh, right, that should be K prime, thank you. Yeah, and here in this curve, in this case, C is defined, yeah, over K. Right, that's a K prime. Mm-hmm. Thank you. Okay, so let's suppose we have a curve, C, that's connected, nodal, and projective over an algebraically closed field. And then we let P1 to P delta be the nodes. So D delta is the number of nodes. In this example, delta is, let's see, 1, 2, 3, 4, 5, 6, 7. And let's let C1 to C mu be the irreducible components of C. And so mu is the number of irreducible components. In this example, it's 4. And then we have GI be the genus of the normalization of these components. So in this example, maybe this is G1, G2, G3, and G4. So these numbers are indicating like the geometric genus, the genus of the normalization. And so let's to compute now the total genus. So yeah, the C tilde denotes the normalization. So let's take the normalization of C. And we know this is a disjoint union of these curves C tilde I. And we're going to use sort of the exact sequence. So we know that that OC and the push, we know that the normalization map is birational, right? It's an isomorphism over the complement of the nodes. So the quotient of this map is sort of just the direct sum of the residue fields of the points pi. And therefore, just taking the standard long exact sequence, you get the following long exact sequence: H0 of C, OC. I'll just write it out. then there's no H1 in the final term because it's a sheaf with dimension 0 support. And so we just look at the dimensions of these components, right? So we're assuming C is connected, so this is one dimensional. C tilde is not necessarily connected. The number of connected components is precisely the number of irreducible components of the original curve. This is mu. And here we're taking the direct sum over all the nodes. That's delta. This is the dimension of this is the definition of the genus of C. And since C tilde is the disjoint union of these C tilde's i's, this is the sum of GI's. And so putting this all together tells us that the genus of C is the sum of the geometric genus of the components plus delta minus mu plus 1. And so in this example, on the right-hand side, if we compute the genus, let's see, we take the sum of the components, 6 plus 1 plus 4 plus 0, and then I'm adding in delta, subtracting mu, and then adding a 1. And this is 7, 11, plus 4, 15. And note that, yeah, and that you can also use this picture to kind of come up with a nice, maybe a way to compute it like very, very quickly. Is that if you just look at like the number of the connected regions here. So there's this region, this region, this region, and this region. There's 4 of these regions. And the genus is exactly that number plus the sum of the geometric genus of the components. 6 plus 1 plus 4 plus 4. Okay. This may be familiar to many of you, but it's kind of, yeah, it's nice to recall. And the next thing we want to discuss is the dualizing sheaf for nodal curves, which is a technical but important notion. Are there questions before I move on?
Are we assuming pretty much always the curves are generically reduced?
Yes. Oh, yeah. Well, a nodal curve. Well, yeah. I guess I didn't define precisely what I mean by a nodal curve. But when I say a nodal curve, I mean a curve over a field such that all of the points are either smooth or nodal, and that implies that it's not only geometrically reduced but reduced. Yeah. That's a good question because we will need to discuss non-reduced curves and families of possibly non-reduced curves where the reduction is nodal. Other questions? Okay, so we're on to the dualizing sheaf. So I mean, a nodal curve, if you think about what the defining property of a node, a nodal curve is necessarily a local complete intersection. And if you've read Hartshorne's exposition of Serre duality, you know that automatically implies that there's a dualizing sheaf, a sheaf omega C that satisfies Serre duality. But we kind of, but we would like to get a more explicit description of this in the case of a nodal curve. So that's what we're after right now. And the reason we want this is because the dualizing sheaf for a nodal curve will be a line bundle and will play the role that the sheaf of differentials played for smooth curves, right? This will give us a line bundle that when we take a sufficient power, will give us an embedding into projective space, and so we can use this. So to define it, we defined it in terms of the normalization. So we consider the normalization of C tilde over C. Let's call that pi. And let's call sigma the singular locus of C. well, I shouldn't use script. Yeah. So this is just the set of nodes. And let's take pi inverse of, wait, let's take, yeah, the preimage, let's just let sigma tilde be the preimage. So our picture looks like this. This is just the case where we have one node and then our normalization. And then there's two preimages of this one point. And in general, like let's use the notation that if Zi is a node, well, we have two preimages, Pi and Qi over Zi. So here maybe a P and a Q over a Z. And so we're going to define the omega C using the sheaf of differentials on the normalization. And we actually consider, so let's consider this exact sequence. So I have the sheaf of differentials on the normalization, and I could also twist that by the divisor sigma tilde, right? Remember, C tilde is a smooth curve. And sigma, this is just a divisor. And the quotient is the structure sheaf of sigma tilde. And we can write this as just the direct sum, let's just say of all points y in sigma tilde of this residue field of y. And we can think about this twist as, note that if you're twisting by a divisor. So if you take this twist, this omega C tilde twisted by sigma tilde, if you restrict this to the complement of sigma tilde, then it's isomorphic to omega C. So these, yeah. So you can interpret sections of this as the sheaf of meromorphic, or maybe I should say rational sections of omega C with a pole of order at worst 1. And then what this map does, it just takes a section, and if you evaluate it at a point y, you get the residue. Well, you get the residue of the section S at the point y. And if you want, you could take this as the definition of the residue. So for instance, if you had a section S such that all the residues were 0, then in other words, then there's no poles, and your section is not just rational. It is a section of the sheaf of differentials. It's a regular section. Right. Okay. So we have this, and then we define. Let's define the subsheaf omega C. So we don't yet know its dualizing sheaf. We're just defining this as an abstract subsheaf of the push forward of omega C tilde twisted by sigma tilde. And find on an open set in C tilde. Oh no, sorry, it lives on C. So for an open set V in C, we set the global sections of omega C as the subsheaf as sections S on inverse of V with the following property that for all nodes, Zi in sigma, that the sum of the residues at Pi, at one of the preimages, plus the other one is 0. All right, that's our definition as a subsheaf. And sort of the definition implies that there's two exact sequences that are quite useful when computing. I mean, the first definition is that is essentially the definition that we have omega c sitting inside the push forward of this where this map takes a section S to the differences of the residues. Is that okay? And then the second one was this is contained in the sheaf of differentials, and the sheaf of differentials is precisely the enlargement such that where a section here S goes to just the residue at pi, which is the same as the residue at qi of S. So the sheaf of differentials, sits in between the push forward of the twist of the sheaf of differentials, the normalization, and just the push forward of the sheaf of differentials. All right, and now we need to get to some of this and some of its defining or some of its important properties. Right, so moving. Joe, let me just copy this definition so that we don't lose it.
Sorry,
Yes.
Can I ask you something? So what is the first map in the second exact sequence?
What is the first map here? Like this map?
No, in the second exact sequence. The second sequence, the first
This
map.
one.
The first one.
Oh, well, I think it comes from the fact that if you have a regular sheaf of differential, if you have a regular differential on the normalization, then it's also a section of omega c by definition, right? If you look at it follows from this definition here that if you have S, if it's
sorry, yeah, yes.
That makes sense. Okay.
Thank you. Sorry.
Right. So I recall here we have the definition again, just to keep it on the same page. And I want to do one example, and this is actually seems like a very simple example, but in fact everything can be reduced to this. So let's take a planar singularity. Let's take the union of the two axes inside A2. So this is just, and let's take its normalization, which is going to be the union of two axes. So here we have a singularity, and the normalization is just two copies of A1, right? We have one singularity, which is 0, and its pre-image is, let's just call them P and Q. And let's realize that that K, X, Y, that the induced map on rings here, that this is the subring of functions f, x, and g of y that agree, so whose value such that when you evaluate them at 0, they're identified. Right, a function on the normalization descends to the nodal curve if the evaluation at P is equal to the evaluation at Q. Okay. And so maybe an example of a differential would be, let's let mu be dx over x minus dy over y. This is certainly an example of a global section, because the residue of of this is 1, and the residue of this is -1. But let's suppose we have an arbitrary, let's suppose we just have an arbitrary section, f of x dx over x, and then a g of y dy over y. And let's put a minus sign here, just, suppose this is a global section. So any global section can be written of this form because we know the poles are at worst order 1. Right. So this let's realize that this differential, in fact, can be written as, I claim that this, in fact, can be written. This is equal to, if I let me write it this way. Times mu. Hold on. Okay, let me take a step back. Okay. So let me. So yeah, note that if we have this differential here, then necessarily the defining feature is that the residues are opposite. So what that means is that then f of 0 equals g of 0. So this is exactly the condition that the functions f of x and g of y on the normalization descend to a function on the curve, and what it descends to is precisely this function here. So then, yeah, so this differential then is these two are equal. This is okay. These are equal. And what that means then is that omega c on this curve is isomorphic to OC with generator mu, or nu, sorry. Yeah. So in this basic example, you can write down exactly what the sections of the dualizing sheaf are, and you just show directly that that this sheaf is trivial, and with generator given by nu. All right. And so why is that so important? It's because we know Ital locally, all nodes look like this. So this is the important calculation. And then you can use, but you need to know that if you have an Ital cover of a curve, then the dualizing sheaf pulls back. So I leave this as an exercise, but the fact you need to know is that normalization commutes with Ital maps. So it's, once you know that, it's just a simple consequence. And therefore, because we know nodes Ital locally look like this, we get that omega c is always a line bundle on a nodal curve. And then maybe the most important fact is that the way we've defined omega c is the dualizing sheaf. So the exercise is to use Serre duality for smooth curves to show that omega c is a dualizing sheaf. I think there's no way to directly prove it. Serre duality for smooth curves is a deep result, and I think the easiest way to get at this is to reduce it to that using properties of the normalization. Any questions?
So it's just a property of normalization that every node has two preimages?
Yeah. Yeah, exactly. Right, the last property we need is the local structure of nodes, and I want to do this in families. So this is, this is the last part of today's lecture. And to begin, so I have the desired statement on the right-hand side, but in order to motivate it, let's just recall like the local structure of smooth points of curves. And so suppose we have a smooth family of curves, and then if you have a point, any point, then a tau locally on S and on the total family C, it looks like just A1. So maybe I point out that this is commutative. It's not necessarily Cartesian. You may need to take, this is a statement that's it's a tau local. You have to take a tau covers both on the base and on the source. But then the C prime is a tau over A1 over S. And so this is, relative affine space, of dimension 1. And, it's also the pullback of just the map from A1 Z over spec Z. So hopefully this is a familiar fact. In fact, this follows just from the local structure of just smooth morphisms. Any smooth morphism has such a structure. Any smooth morphism is a tau locally this like equal to affine space of the corresponding dimension. All right.
Quick question.
Yeah.
So where does P show up? Is S prime just like a neighborhood?
Yeah. So right, that's a good point. So so you have your point P in C. There exists also a pre-image of this, and this P prime should map to 0 in here. Or the corresponding 0 over the fiber of the image of P prime and S prime. Thanks. Okay, so we have an analogous result for the structure of nodes. So here I haven't defined what a family of nodal curves is, so I'm just gonna state the precise hypothesis we have. So C to S,
excuse me,
is.
Why did you choose an Nodal neighborhood of C over S? Isn't it enough to take Zariski neighborhoods for the smooth? Like it's a tall over it's a tall over A1, but isn't it Zariski locally a tall like it's a Zariski
you're right.
locally it's Zariski locally standard smooth?
Yeah, good. Yeah, I think Ben's making the important point that there's even a stronger statement here, but I'm sort of stating it in a way that's just gonna, that will generalize.
Oh, okay. I see.
Will be in the same form for nodal curves. But yeah, that's a good point, because there is a stronger result that these maps, you can take them to be Zariski opens. Right, so we starting with a morphism pi, and it's a flat and finitely presented morphism such that every fiber is a curve. And I take a point P and C, which is a node in the fiber of CS. In particular, like by our definitions, like it's a reduced point in the fiber. And then the conclusion is analogous, that there's a tau neighborhoods, where this diagram again is commutative, but not necessarily Cartesian. We have a tau neighborhoods of Fs and a tau neighborhoods, the total family C, which in turn is in a tau neighborhood of this particularly nice node. And yeah, like note that this morphism is the base change of sort of this universal family of nodes. Along a morphism spec. So there's morphisms from spec A to this where T goes to the pullback, where T pulls back to a function F in A. And so, yeah, this is defined. F and A is a function not vanishing at S prime. At least is the statement clear? So what we like the statement, well, it will imply, it will imply a number of nice properties. In particular, it allows us to know, that the locus of nodes is an open condition in an arbitrary family of curves. And we'll then use that to know that like the substack of nodal curves and the stack of all curves is an open substack. So that's why we want this statement. But hopefully the statement, the statement is clear. All right, so I want to end with maybe a sketch of the proof of this. There's a lot of ingredients in the proof, but I think I can wrap it up in 10 minutes. Okay, so this is the theorem we want, and keep in mind that the very special case where like the base S is a field, that is then that was the statement we had earlier as an exercise of the local structure of a node of a curve. And our strategy is as follows. So the first step is to reduce to the case that S is finite type over the integers. And so note that in these hypotheses, like our morphism C of S is flat and it's of finite presentation. And this is always sort of the hypothesis that you use instead of finite type in the non-Noetherian setting. And to reduce to this, you use a technique called absolute Noetherian approximation. It's very useful, especially in moduli theory, to reduce to the Noetherian case. To the Noetherian case. I'm not going to go through this right now because I don't have the time, but it's particularly nice in moduli theory and important in moduli theory because we're defining our stacks over the like category of all schemes. We can't just restrict to finite type schemes and Noetherian schemes. So when you need to prove something about the stacks, often you need to prove something about an arbitrary family, possibly over a non-Noetherian base, and then so you need non-Noetherian methods. And the most common technique is just to reduce to the Noetherian case. And there's this a technique using absolute Noetherian approximation, where the main idea is that like if S is an affine scheme, then the family of curves C, since it's finite presentation, it's only defined by finitely many equations and finitely many relations. You only need finitely many elements of that ring, of the coordinate ring of S. And so then you get this finitely generated Z subalgebra of the coordinate ring. And basically your family of curves lives over that. And that allows you to reduce, and your family of curves is the pullback of that. Anyway, there's more to say there, but I'm not going to go into the details. All right, that's the first step. And then on the second step, we want to reduce to the case where the completion of the fiber has that particularly nice form. So we want to reduce to the case that the complete local ring at the fiber CS of P is isomorphic to this. And this follows by, the way you show this is you apply the earlier exercise to conclude that there exists a separable field extension of the fiber, but then and a point P prime and CK prime, with the corresponding properties, and then you have to choose, S prime. You have to choose an Étale neighborhood of S, and the way you do it such that you just choose an arbitrary Étale neighborhood such that the induced map on residue fields is the desired, such that this is isomorphic to K prime over KS. So yeah, we know after a finite separable field extension, we can get the node in the standard form, and then you just choose an Étal neighborhood that induces that separable extension of fields. And you can do that essentially by the primitive element theorem of fields. You just adjoin one variable, and then there's a mod out by that polynomial and shrink so that's Étal. Okay, that's step 2. And now we have to go from the complete local ring in the fiber to the complete local ring at P. And this is one of the difficult steps, and when you need to use formal deformation theory. And this is where Schlesinger's theorem plays a role. So I'm not going to spell out what Schlesinger's theorem does in general, but in this context, if you apply it to the local deformation functor of a node, it says the following. It says that if you're given, so we have our family CS, yeah. Let's let KS just be K for convenience. So we have our curve, and suppose you have some deformation of this, so some maybe spec B, some curve D over this, a flat family, such that this is Cartesian, and B here, it could be local Artinian, or it could be complete. Given that, the Schlesinger's theorem implies that that this is a pullback of T x y mod xy minus T. Of this family of curves with nodes. In other words, it says that every local deformation of a nodal singularity is the restriction of this particular one. Like this one-dimensional deformation of the node captures all possible deformations. And then we apply this theorem. We apply this to, so here I have my curve. And I apply it to the restriction of the complete local ring. And what it gives me is it gives me a morphism to, well, let me cheat, to here. Such that, and T here then pulls back to some function F. And since it was a node, this function F is non-zero at that point S. And the completion of this at this point is identified with the completion here. So you get, so this completes the third step. So it essentially follows from Schlesinger's theorem, which we have not covered, but it's that's a nice topic that deserves some attention, but we can't cover everything. All right, now putting everything together, and now we need is following fourth step. So to remind you, I've written the theorem again to remind you of what we're trying to prove, and so far we know that the complete local ring of C has this nice structure. And we need to go from the complete local ring to an Étal neighborhood, and we use the powerful result of Artin approximation. Artin approximation is a technique to go from properties of the completion to Étal neighborhoods that we covered in one of the earlier lectures. I recall the statement here, and let me tell you how we apply it. So let's define a functor F from schemes over S to sets, where the scheme T over S goes to sort of all to the set of diagrams. And where T maps to spec Z T, and this maps to spec And so this is our functor, and because C over S is locally is a finite presentation, you can check that this functor is limit preserving. And we know that over, you know, if T is the completion of S, we have an object over this. I mean, this is exactly what we kind of constructed over here. We have this, and in fact, let's just remove the completions. And so this here defines an element sigma hat of F over O hat SS. And then R in approximation gives us the desired diagram that we wanted. And then moreover, that gives us the desired diagram. And then to show that this is a tau, you use the fact that we know that, note that R in approximation only gives us an approximation, right? You apply R in approximation with n equals 2, but yet that's enough to conclude that this map is a tau, because we're going to check that induces an isomorphism on completions. We know that the two completions are abstractly isomorphic, and we know that the map induces an isomorphism mod the second power of the maximal ideal. And then you use this fact that the Noetherian rings, or surjective endomorphism of Noetherian rings, is an isomorphism. And to check that a map of complete local rings is surjective, it suffices to check on the second power of the maximal ideal. But in the end, that guarantees a tauness, and that gives us our local structure theorem, relying on this powerful result of R in approximation.